Okay, recording is rolling. It's Monday, April 24th, and we're going into the last main topic that you guys are going to learn in this class, which is going to be quantum mechanics. Now, I'm going to lead into that with some statistics. So I just gave you guys a pack that looks kind of like this. Right? Reason being that quantum mechanics requires a different type of thinking than we've been doing, like from anything we've done this year up to last week. So far things have been very formulaic. You throw a ball at some angle so fast, like where does it land? Kind of okay. I got some formulas. I got a process. I can plug stuff in. Okay? Quantum mechanics is more like a probabilistic. Right. So I want you guys to have at least some kind of statistical foundation, at least just have the framework to think probabilistically. Right. So we're going to do that. Uh, and we've been doing quantum mechanics last few years. Work, working pretty good is I'll show you guys a bunch of topics within quantum mechanics and have you guys keep a journal. I'll go over with you guys piece by piece. And just have you guys turn that in. So I'm not going to be here tomorrow. There's a appointment I have to go to. Sorry about that. So tomorrow's going to be a little bit of an off day, but then we'll pick up on Wednesday and move on from there. Okay. Oh, speaking of Wednesday, okay, here's more school type stuff. Hold on. If you are taking any AP classes, that some of you guys are, then on Wednesday, they're going to have you in the cafeteria one of these class periods to fill out your label sheets. Right, so freshman period 1, sophomores period 2, juniors period 3, and seniors period 4. And this is going to be on Wednesday the 26th. I'll be in the cafeteria just filling out bubble sheets. Okay. So you know that. Right. And since we're coming to the end of the year, we've got schedules for AP exams, final exams. I did post these to Google Classroom. I got the May calendar. School administration gave this to us. I posted this to Google Classroom, and also the final exam schedule, which is a couple pages there. Right? So let's look at that real fast so you guys know what's coming up. Okay. The first couple of weeks in May are AP exam weeks. If you're taking an AP exam, you guys know what's going there. Like I know the physics 1 exam is going to be on Thursday the 11th because that class I got to do myself. Okay. Uh, Tuesday, well, I should say the next few days after that are senior exams. So the 15, 16, 17, those are going to be senior exams. I know specifically Tuesday the 16th are science classes, our final exams. Now that's just for seniors. So if you're a senior, I know I've got a few seniors in here. Okay, be looking for this about mid-May. Okay, now everybody else, so all my sophomores and juniors, you guys are gonna have your final exams like the last week in May, so the 23rd to the 26th. So this is going to be well here. So the 23rd is period 7, and then after that goes period 6, 5, 4, 3, 2, and 1. Okay? And then on the 26th is also graduation day. That's what this graduation cap is about. All right, so you guys good with what's going on in this class about next week or two, and what's going on in school for about the next month? All right. Yeah, we are winding down. We are coming to the end. Okay. So we're going to do quantum mechanics, and then I'll do a final exam review with you guys. That'll be in time for the seniors to take their final exam. All right. Then everybody else, we're going to do little fun stuff projects. All right. Oh, yeah. Oh, need that. Okay. Okay. Anybody not have this packet? Does anybody not have this packet? Okay, so everybody's got one? Let's go on. All right. So, quick show of hands. How many guys have taken stats? Taken a stats class? Stats class. Okay, a couple of guys. All right. All right. So, I at least want to introduce you guys to things like probability, statistics, normal distribution. Right? So, I've got a few examples lined up of populations. Right? So you guys have populations of dogs, populations of people, and populations of trees. Right? And let's say I'm interested in height, right? Like heights of dogs, heights of people, heights of trees. Right? Now think for a moment of two concepts. Right? One is like average height, right? But also think about like variability. Right? I'll bring in an idea called standard deviation. Right? So let's just focus on dogs and people for to start with. Okay? Guys, on average, what's taller, the average person or the average dog? Average person. Average person is taller. Right? So if I asked you to like find the mean height, you would expect the mean height for a person to be greater than the mean height of a dog. That makes sense, right? But now think in terms of sort of like variability, right? Like let's just say we're looking at adult people, some kind of control population. most people are kind of about what, 5 or 6 feet tall, right? There's not a whole lot of variability beyond that, right? Maybe a little bit, but not a lot. Right? Most people are like 5, 6. Oh, you have a question? Oh no, okay. Right. But think about dogs. Dogs, it's crazy. They're all over the place, right? You got little tiny short dogs. You got little poodles. You got Great Danes. I mean, huge variability in size. If the same variability of dogs apply to people, right? Think about how crazy that would be, right? Like how short and tall people could be, right? Right. So I also got trees in here, and then this won't just apply to like heights. It applies to like all sorts of things in nature have some kind of a bell curve distribution. Okay, you see that? Okay. Oh, in fact, let me draw sort of a graph of this, right, just to get the idea down. Okay. Let's say you pick some population like people, right? You look at height of people, right? Now let's say I have them in 5 categories. Got average height. I got a little bit bigger than average. I got super tall people. I got a little bit shorter than average, and I got super short people. Okay, right? Just to get the concept across. Right? And then I made like a bar graph. Like what's the population size or proportion or something. Right? Population size, proportion. Okay, and then maybe we'll say proportion. How about that? Proportion. Okay. Now average people. Well, that's probably probably a good part of the population. Maybe like the plurality could be like somewhere in the middle, right? Kind of like an average height. Now, how many people are a little bit shorter than average? Well, probably not as many people. Okay? How many people are like super short? Maybe a few, maybe something like that. Right? How about how many people are like a little bit taller than average? Again, not as many as there are average, but not a huge drop off, right? How many people are like crazy tall, like could like 7 foot tall playing basketball? Maybe like a very small proportion of the whole population, right? Right. Now, this is with 5 categories. You could do 10, 15, 50 categories if you want, right? And the more granular you get, the more what's going to develop is this bell curve type distribution, right? Where it's going to guess it's like bell curve. Okay? Right. Now, this average part, I'll call this the mean or the average. You'll see 2 symbols that are used for this. Right? You'll see an X with a bar over it. I'll call that X bar, right? Or you might see mu. Okay, I'm going to use those interchangeably. Once for a population, or once for a sample, once for a population, but I'm not going to get that detailed. Okay? So this could be like some kind of average, okay, like a mean average. Okay? Now another thing is, think about that variability I was talking about, like that plus or minus factor, like people compared to dogs. Right? Do you guys see the middle part of this graph looks what you might call like concave down, and the tails look kind of like concave up? You guys see that? And there's a point where it switches. Well, I guess there's a point there and there's a point here, right? Now, if I don't just have 5 bars, but if I had like 50 categories instead of 5, right? You might see a place where it actually switches over. Like, oh, exactly, I don't know, like 5'8" or something. Okay, I guess that. Well, I wonder what is this spacing right here from the mean to that inflection point. That's what this is, right? An inflection point. Right? What is that? What is that distance, right? And that distance has a name. It's called standard deviation. Right? And I'm going to represent this either with an S. S's are tricky because it might look like a 5, but an S. Right? Or you might see the Greek letter sigma. Okay? Okay. Again, if you take a stats class, there's technically a difference between those two. I'm not going to really split hairs today, but I might use those interchangeably. Okay? You guys got that idea? Right? It tells you something about, all right, but how varied is the state? I'll call it standard deviation. Okay? Pretty good so far? All right. Now let's look at this packet because we're going to crunch some data. Now, let's say we have a sample of 5 for each of these populations. It's supposed to be representative of the population as a whole. Right? Now, just like normal, my numbers are different than your numbers, but we're going to use all the same processes because it's all the same stories attached. Okay? Okay. I gave you guys a couple of formulas up here. One is to find the mean. Now, you guys have taken the mean just in this class. I mean, you guys know the mean before you walked in this class, right? You just add up all the individual values and divide by the sample size. You guys see that? Okay? But there's also an expression to tell you how to find this right here, the standard deviation. We're going to walk through each one of those. Right, you guys ready to do that? Ready to walk through? All right. So let's start with these 5 dogs. I want to know what is the mean height of the dog. So I'll say X bar equals. Just for completion, I'll go ahead and write it out. Now my dog heights, I have 66 centimeters. You guys are doing it as I'm doing it. I have 75 centimeters. One dog's 91 centimeters. One dog is 103 centimeters tall, and my last dog is 112 centimeters tall. Okay, those are my 5 dogs. Okay, and then I'm going to divide by 5 dogs. Right? Let's see, what does this come out to? What is that dog plus that dog plus that dog plus that dog plus that dog, all divided by 5 dogs? That's telling me this many, and the unit would be centimeters, right? So I have an X bar, or you could say mu or X bar of 89.4 centimeters. Okay? That's like the average dog height. So I'll go to this box and say this many centimeters. Okay. Now, don't copy my number because your numbers are different than mine, but do you guys have a number in that first box? We got that? We good? Good. All right. Okay. You guys ready for the standard deviation? Okay. Now the standard deviation, here's what I do. It's going to take a bit of paper, so I'm actually going to flip this paper over. Okay. I'm going to write my X bar up here. X bar is 89.4 centimeters. Now hold on to that number, because we're going to use that. Okay. Now this is going to be a whole process. You guys ready for this process? Okay. So I'm going to say, well, okay, I'm going to say S. S equals. Right? Now here's exactly what it says to do. It says to take each individual sample, that's what X of I is, so each individual dog height, okay, subtract the average, right? Square that, add up all the differences. So since I have 5 dogs, I'm going to get like 5 differences. I'll square those 5 differences. Now, anytime you square something, it makes it positive, right? So like if you didn't square it, then at this point, it would all zero out. It would have to. So part of the point of squaring it is it doesn't zero out. Okay. Then I'm going to divide by the number of dogs minus 1. Now, this is a weird, tricky concept. It has to do with degrees of freedom. So however many dogs you have, subtract 1, that's your degrees of freedom. Okay? And then finally, I'm going to take the square root. Think of that sort of like undoing the square. Right? At some point in the process, I squared, and the square root. Okay, you guys get that? So what's that going to look like with the numbers thrown in? Well, here's my dogs. 66 minus 89.4, square that, plus 75 minus 89.4, square that, plus 91 minus 89.4, square that, plus 103 minus 89.4, square that, plus 112 minus 89.4, square that. Okay.
Which value is 89.4?
That is the average. Average, yeah, there you go. Okay. Okay. So I've taken the 5 differences. I've just added them all up, so that takes me to the sigma. Okay. I'm going to divide that by the number of dogs minus 1. So I had 5 dogs, so 5 minus 1, say, divide by 4. Okay. And then finally, I'm going to take the square root of all that. Okay. Now, if you like, you can chunk that into smaller steps in your calculator, but do that. Okay. So that minus that squared plus 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 that minus that squared. Oh, whoops, ran out of room here. All right, and at the end, I'm getting a number. Okay. And that number is also the same unit as we've been working with all along, so centimeters. Right? Again, think of this like kind of like a plus or minus factor. Right? And that number goes into the second box. Maybe I'll round it to like that. How about that? Okay. All right. Are we good? So your first box, you have the mean, the average, which you've probably known how to do for years. The second box, you follow this process and you got the standard deviation, which tells you how far from the mean to this inflection point. And think of that kind of like a plus or minus factor on your dog size. Right? Now, not all dogs are going to fit within that plus or minus, but I'll tell you what, about 68% of dogs will, if these dogs are representative of the dog population. And you have a few out on this tail and a few out on this tail. Okay. Okay. All right, you guys good? We're good? All right. All right. Now, turns out that everything that we did so far, your calculator can do for you. So pull out the calculator and make sure you have this model calculator. I've got like 30 of these calculators going around. Everybody got this model calculator? Unless, of course, you've taken stats and you're familiar with how to do this process on a different one. That's okay. You guys ready? Okay. Now, we need to reset the data because we've been crushing numbers in my other class. So here we go. Hit second, reset. You guys see the zero is the reset? Did you guys hit second reset? And it says, do you want to reset? No or yes? And you're going to scroll over to yes. You guys see that? Okay. So you hit second reset. You're going to scroll over to yes and hit enter. Right. It should say memory cleared. Everybody clear their memory? Everybody clear the calculator memory? Okay. Right. You guys ready for this? Right. Now I'm going to show you that the calculator will give you the same numbers. You guys ready for this? Right. Hit second stat. You guys see this key that says data, but right above it says stat? Well, if you hit second and then the data key, it'll actually pull up stat. It should say one variable. Do you guys see one variable? Right. Hit yes, I want one variable. One variable. Okay. Right. Now your calculator is ready to take statistical data. See where it says stat on the screen? You guys see stat? Right. 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 Anybody got a question? Right. Now hit the data key. The data. You guys see data right there? Bam, data. It should say X1. Okay. Does anybody not see X1 on their screen? Does anybody not see X1? Right. All right. Listen. All right, so everybody's got X1 now, right? Everybody's got X1? All right. All right, now let's punch in these dogs. All right, so my first dog was this many centimeters tall. You guys got your first dog punched in? Scroll down, frequency 1. Yep, there's only one of those dogs. Scroll down again. X2, my second dog was this many centimeters tall. Scroll down, yep, there's only one of those dogs. Frequency 1, scroll down again. X3, my third dog was this tall. Scroll down, scroll down. My fourth dog was this tall. Scroll down, scroll down. My fifth dog was this tall. Okay. Now I have my 5 dogs loaded into the calculator. You guys got your 5 dogs in the calculator? Okay. Now, do you guys see the key that says StatVar? You guys see StatVar? Okay. Hit that key. Okay. And should pop up this on your screen. Okay. Does anybody not have that? Everybody's got that. All right, nice, nice. You guys are doing awesome. Okay. N is 5. Yep, have a sample size of 5. That's 5 dogs. Scroll to the right. X bar. Hey, look, that number matches that number. You guys see that? Right? It just told you the average. You guys got the average? Right? Now, the 2 to the right, I said I'm going to use these interchangeably. See where it says S sub X and sigma sub X? Right. Now, there's a technical difference between those two. We're just going to use the S, okay? Because we were doing for samples. Hey, look at that. That's the same thing I got by doing this by hand. Actually, before I rounded, I actually got 19.06 centimeters, okay? For like the plus or minus factor. Okay? Do you guys get the same number right there? You guys got the same thing? Right? Are we good? Right. Any questions so far? Any questions? Okay. All right. So now you know how to use the calculator to tell you not only what is the average of some sample, but also like how spread out is that data? What is the standard deviation? Okay. Oh, yes.
So every time you want to put in new numbers, you should clear the data.
That's usually a good idea. Now I'm just going to override what's there for as long as we only. Okay, but yeah, that's usually a safe thing to do because sometimes like if you have more than 5 samples and you go and put in 5 samples, then the other data is like lingering there. So yeah, if you clear it out, it's usually a safe thing. Okay. I'm just going to override what's already there though because I've only got 5 here and 5 here. All right, so you guys ready to do it for 5 people? Okay, so go back to data. Okay. Now my dog data is already there. Again, I'm just going to override it. So my first person is this many centimeters tall. Scroll down. Yep, there's only one of those guys. Scroll down again. X2. This guy's this many centimeters tall. Scroll down. Yep, there's only one of those guys. Scroll down again. X3. This guy's this centimeters tall. Scroll down, scroll down. this many centimeters, scroll down, this many centimeters. Okay. Now I have 5 people input. You guys got 5 people input? Okay. Hit stat var. And this 5, yep, I got 5 people. Scroll to the right, X bar. Right, so my average person is this many centimeters tall. Okay. Scroll to the right again, and sort of a plus or minus factor. Maybe I'll keep an extra digit, I guess. Maybe I should have done that all along, for like an extra digit. Okay. There's my standard deviation. Okay. Are we good? All right. Ooh, now I have 5 trees. You guys ready for the 5 trees? Okay. Now, wait. I'm not ready for the 5 trees because there's a concept I want to point out. Okay. Remember when I started this, we were talking about comparing these 2 populations, like dog heights and people heights. Okay. So you guys told me that the average person should be taller than the average dog. And look at that. The means do show that. Right? The average person is taller than the average dog, and that should be also true on your paper. But then I asked you guys a question about variability. I said, well, who has more variability in their sizes, people or dogs? And you guys said what? Dogs. Compare these standard deviations. Oh, look at that. Do you guys have a larger standard deviation on your dog sizes than on your people sizes? Right? You should. You guys got that too? Right? Right? Because people are more like uniform comparatively. Right? Right. Now I'm ready for trees. Now, I made it some crazy tree example. I don't know. Maybe these are all the same species of tree. Maybe these have been selected for Christmas trees. Maybe these are like Christmas trees to be sold off the lot. So whoever selected these trees is trying to choose the same heights. Now, they aren't exactly the same, like down to the millimeter, but they're pretty close. So there's not a lot of variability. Let's plug in these trees. So my first tree, so hit data. My first tree is this many centimeters tall. Scroll down, scroll down. My next tree is this many centimeters tall. Scroll down, scroll down. My third tree is this many centimeters. Scroll down, scroll down. Fourth tree, scroll down, scroll down. Fifth tree. Now I have my 5 trees in my calculator. Hit stat var. Yep, I have 5 trees. Scroll to the right. My average tree is this many centimeters, right? Scroll to the right. And here's my standard deviation. All right. Who's got any question? Any question? Is this working out for you guys? All right, nice. All right. Now let's look at these bell curve graphs. Okay. So these are sort of representative of the 3 samples we were just looking at. Right? We've got dogs, people, and trees. Do you guys see increasing height is going to the right? So maybe these could have been bar charts, but just made like bell curves. Right? So going to the right is increasing height. Okay. And then some of these are like more spread out. Some of them are like bunched together. So which curve represents, so out of dogs, people, and trees, in terms of their heights, which curve represents the shortest height and also the greatest variability? Which one is that? I'm thinking it's dogs. Look, dogs has not only the smallest mean, but also the greatest standard deviation. So here's dogs. Go ahead and label this dogs. You guys label that dogs? Exactly like it says in the directions. Label it dogs. Okay. Now, which one's kind of in the middle, right? Has like the medium height, but also the medium like variability. There's your people. Right? And then see, if you look at your trees, right? I made the trees really tall, which means it's furthest to the right on the graph, but it also gave it hardly any standard deviation at all. Right? It made all the trees sort of the same height. Right? So wouldn't this have to represent trees for both of those reasons? Right? It's furthest to the right, and also they're bunched closer together. Right, you guys got that? Right, are we good? Right, any question? All right, this next part. All right, so now I'm going to introduce a new idea to you guys called Z-score, which here, let me flash forward a little bit. If you look on the back of your packet, you might see a couple of bell curves with a big old table, and the table is in 2 halves. Guess that? Right. So what we're about to do is going to link to that table eventually. Okay. So a Z-score is like within your own population, sort of where do you land? Sort of proportionally, right? this way you can compare like dogs, people, and trees. Even like if you have a single dog, a single person, a single tree, okay? You say, is the single person like taller than or shorter than average compared to all other people? What about this or that dog? Where do they kind of fit within their own population? So Z-score will tell you where you land within your own population. It sort of standardizes the data so that it doesn't matter if we're talking about like different populations with different average heights or something. Right? So I'm going to take the individual sample. I'm going to subtract the average. Right? Oh, look at that. If you're above average, wouldn't this already be positive? And if you're below average, wouldn't this already be negative? Right? Just think ahead a little bit. Right, that's going to come back later. Then I'm going to divide by the standard deviation. Isn't this like a count of the number of standard deviations? Right? So this is like the number of standard deviations from the mean. Right? And this is for like a single individual. Right? So for an individual. Right? You guys see that? Right? Or I might write it this way. So I might do an individual sample. I might say minus mu over sigma. Again, I might use these notations interchangeably. Take stats, you can kind of split hairs and say there's technically a difference, but okay, guess that. So let's see. My first dog is so many centimeters tall. Where's that dog fit within the population of dogs? Is this a tall dog, a short dog, and how tall or how short? Okay. Well, we can use this right here. So let's try this out. So my first dog is this many centimeters tall. I'm going to subtract the mean, which is this right here. That's all centimeters. Okay. And we're going to divide by, well, here's like the plus or minus factor, or the standard deviation for a single dog. Right? Okay. Let me say, what is the Z-score for this dog? Do you guys get a Z-score? And our Z-score should land somewhere between -3 and 3. Technically, it could be outside that window, but that starts to get pretty extreme. Right? So, I gave you guys multiple choice. Does it match one of your multiple choice answers? Matches your multiple choice? Okay, are we good? Okay. Let me do that for my next dog. My next dog. You guys are following along? You guys see the pattern. We're just going to do all 6 of these individuals. Okay. My next dog is this tall. So take that height, subtract the average. Now I can already see that this dog is going to be taller than average, so he's going to have a positive Z-score. Positive Z-score means greater than average. Okay. But how much greater than average? Well, that depends. What's sort of the variability? Okay. So what's the standard deviation? Okay. So I'm getting a Z-score on that dog. All right, let me find. Yep. Bam, multiple choice matches. Okay. Yeah, go. These are matching your multiple choice options. Okay. All right. Then number 5 and number 8, I got 2 humans. So see for right. My first human is this tall. Subtract the average. Okay, and divide by the standard deviation. Okay. Now, since this is a short guy, he's going to have a negative Z-score. Okay. In fact, this guy, at least for how my numbers are panning out, he's really, really short. So he's got a really big negative Z-score. Right? Getting close to -3, which is like extremely short. How about my next guy? My next guy is exactly average. Hey, what does that mean if you're exactly average? 0, right? The numerator zeroes out. So it doesn't even matter what the standard deviation is. Of course, it has to come out to 0. Right? All the units cancel, by the way, so that these are unitless values. Like Z-score could apply to like anything that's normally distributed. So all the units are going to cancel out. All right, let me do my two trees. So I got a tree of, all right, I got a tree that's this tall. All right, here's my average tree. And then the standard deviation of my trees. Okay, let's see how we're looking here. Okay. Ooh, that is a pretty short tree. Okay. I would know that within the population because that's a pretty hefty z-score on the negative side. Okay. And then my last tree. All right. Are you guys getting to your last tree also? It's working out for you guys? You guys are getting all the multiple choice? All right, let's see what this is. Bam. All right. So I'm set. There you go. There's z-scores. All right. You guys doing good on your z-scores? Every good? Every good? All right. Questions so far? Questions? All right. All right. So next page. That was stats part A. All right, let's move on to stats part B. You guys ready for stats part B? All right. All right. Oh, look, it's that bell curve again. Do you guys see the 7 numbers underneath it? Hey, those are z-scores. In fact, I might even label those. Those are z-scores. Right. You go from -3 to +3. You see that? Right. Now, your z-score, again, it tells you how many standard deviations you are from the mean. So it tells you kind of where you land relative to the entire population. So a z-score at -3 or +3 is pretty far out on the extremes, either like crazy short or crazy tall in the examples we've been using. Right? You guys can see that now? Right? And this bell curve tells you more info. It tells you what percentage of the data is within any particular values. Right? So this is one of the first things you'll learn in stats also, is that ±1 standard deviation from the mean, like to that inflection point where it switches concavity, right, contains 68% of the data. And if you go out from there, it contains 95% of the data. Right? And then out from there, it's like 99.7% of the data. So 99.7% of any data within any population that's normally distributed, right, is within 3 standard deviations of the mean. Okay. Right. And there's a tiny, tiny bit that's like out on the tails. Right. There might be like someone out in the world that's like 7'5", but like hardly anyone. Okay. Right. You guys got that? Right. Okay, so same formulas we've been using so far. Now let's apply this to 2 liter, some liters of bottles. So let's say maybe you're working for a consumer protection agency, and you want to say, is there truth in advertising? Some company says they're like filling up some bottles, so you grab a bunch of bottles off the shelf to test this out. Right? Now, how are the bottles filled up? Well, there was some machine at some factory that's going bleep, 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 and was every single bottle receiving exactly the same number of atoms of liquid? Well, no, that'd be crazy. There's a little bit of a plus or minus factor. Okay, so that's what we're about to crunch. Now, I gave you guys 6 bottles. All right. Now, I did throw in a little twist here. I don't know. I wish I hadn't done this, but we got what we got. All right. Do you guys see I gave all the bottles in liters, but I asked for the questions in milliliters? Do you guys see that? Guys, how do you go from liters to milliliters? Multiply by 1,000, right? So I'm going to change all the numbers to be milliliters. So 1.97 liters. Isn't that 1970 milliliters? Okay. And this could be like 1980. This could be 1980 again. This could be 2000 exactly, 2000, and 2010. Can you guys do that? Multiply all your bottles by 1,000 to get milliliters. You guys can do that. Okay. All right. Let's go to data. Let's start plugging these bottles in. So my first bottle is this many milliliters. Scroll down, scroll down. Got this many milliliters. Scroll down, scroll down. This many, scroll down, scroll down. This many, scroll down, scroll down. This many, scroll down, scroll down. Now we have a 6th bottle. which is this many milliliters. Okay, so I got 6 bottles on this that I just pulled off the shelf. Okay. Hit stat var. 6 bottles. Yep. Everybody's got 6 bottles on their screen. Everybody's doing good. Got 6 bottles. Scroll to the right. X bar. Up the mean volume. That's right here. That's what X bar is. The mean. If you guys do X bar equals, it gets that right there. Scroll to the right again, standard deviation. I'll call that S equal maybe S of X. How about that? And 15.5 milliliters. Call it. Okay. You guys get that? Again, that's kind of like a plus or minus effect. Here, if you took your average plus or minus that standard deviation, that should cover 68% of all the bottles. Right? You guys can see that? All right, we're good. Who's got questions so far? Questions so far? All right. All right. Z-score. So I have a single bottle that's this many milliliters. How does this bottle compare to all the other bottles if all the other bottles are representative of the population of bottles? So I'm going to say Z is, I'm going to take that individual bottle, or Z scores for an individual. Okay. I'm going to subtract the mean, which is that number right there. I'm going to divide by the standard deviation. Right? Can you guys do that too? Right. Who's got questions so far? Questions so far? Right. Yeah, you guys are doing awesome. You're doing awesome. So let's try that out. What's that many milliliters minus that many milliliters, all divided by that many milliliters? Right? Milliliters cancel. Right. You should end up with an integer value here, or something really close to an integer. I was trying to make these numbers come out to integers just for this part. Does everybody have an integer? Everybody's got an integer. Is that working for you guys? Okay. Okay. Now, the fact that you have an integer, like I have a z-score of 2, that tells me I'm landing right there. So my bottle has an extremely large amount of liquid compared to most other bottles off the shelf. Okay. So the next question is, how many bottles contain less liquid than this bottle? Wouldn't that be all this part of the curve up to that z-score? Right. So I can add these percentages. So this tiny tail is 0.15%. The next tail is 2.35%. The next bit is 13.5%. The next bit is 34%. Then there's another 34%. It's like mirrored. Okay. Then in 13.5%. Okay. And that will take me up to a z-score of 2. So I'm adding up all those bits of the curve. Oh, whoops. Did I just clear that out? Oops. Turn that off. Let me try again. 0.15 plus 2.35 plus 13.5 plus 34 plus 34 plus 13.5. Okay. And that's telling me 97.5%. Okay. If you have a z-score of 2, then you should match mine. If you have a z-score that's anything else, you just use the same technique I just used. Okay. Does everybody see that? All right. Who's got a question? Who's got a question? Right. Oh, yeah.
So what percentages do you base it off of?
Okay, see this curve up here that tells you what parts of the curve have what percentages? Right. Since I have a z-score of 2, see a z-score of 2? See the numbers beneath the curve that tell there's a 2 here. See the 2? Right. So the question is, how many, like, what percentage of bottles contain less liquid? Right. Well, all of these bottles to the left of 2 contain less liquid. So I add them up. 0.15 plus 2.35 plus 13.5 plus 34 plus 34 plus 13.5. Those are all percentages. And all those numbers add up to 97.5%. Okay. All right. That working out? All right. Now let me show you guys something else, because I'm trying to get to introducing the z table on the back also. Now, z table is in 2 halves. The left half is negative z-scores, which means less than average. The right half is positive z-scores, which means greater than average. Right now, again, you should have like an integer value z-score. My z-score is 2, and do you guys see? It tells you exactly what the table refers to. It tells you the accumulated percentages, like how many are less than, which is the same question we just answered, right? Is what these are set up to answer. Right? So I'm going to go to a z-score of 2.0, which is right here. You guys see under z, I can go down to 2.0. Bam, right there. There's a z-score of 2.0. Right, do you guys see that? Right. Now, of course, you guys care about your own z-score. Right? Now you can get more granular going to the right. You guys see the columns go 2.01, 2.02, 2.03, 2.04, 2.05, all the way to 2.09. You guys see that? Right. So I want 2.0 exactly. And do you guys see the number it says right here? It says 0.977. Right? Or for you guys, whatever your z-score is, it'll tell you the accumulated percentage is up to that point. Right? Now it says a decimal. 0.97. Yeah, 0.977 is that same thing as 97.7%. That's what that would be, right? Okay. Which is actually a more precise value than this bell curve right here. This bell curve, yeah, they're rounded a little bit. Right? The z table is more accurate. But otherwise, like other than the little bit of rounding, you guys see that those are basically a match? You guys see that? Right. And same thing should be true for yours. It should either be exactly the same number or extremely close like mine was. Right? Are we good so far? Are we good? Any question? Any question? Yeah. You're good?
Yeah, I ran into the decimal.
Ah. Okay. So, all right. So you're good. Good deal. All right. Let's just we're gonna do a fast version of this. Does everybody know their height in feet and inches? Everybody know their height in feet and inches? Great. If you don't, just make a guess. I know I'm 5'10". So guys, type in your height in feet. Now, guys, how do you convert from feet to inches? Multiply by 12, right? So 5 times 12, I'm that many inches tall plus the additional 10 inches. So there's 5'10". That's that many inches tall. All right. Does everybody have on their calculator screen right now how many inches tall they are? Everybody got that? Okay. How do you go from inches to centimeters? Times 2.54, right? That's an exact definition, by the way. 1 inch is defined as 2.54 centimeters. Okay. So I'm going to round to the nearest whole number of centimeters. Okay. So guys, write in your height in centimeters to the nearest whole number. Everybody got that? Everybody got their height in centimeters? Everybody got that? Right. We're going to make up 4 friends because I know we're running up pretty close to near the end of class. Make up 4 friends. I got a friend that's this tall. 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 Did you guys just make up 4 friends? All right. All right, you and 4 friends. Okay. All right. Now let's clear out the data because we still got those 6 bottles in the calculator data. Hit second reset. Did everybody just hit second reset? Scroll over to yes and reset their data. Everybody just cleared out their data, right? Or clear out the data. Now let's go to second stat, 1 variable. You guys got second stat, 1 variable? Hit data. You guys see X1? Let's punch in these 5 people, you and all your friends. I'm this tall. Scroll down, scroll down. My friends are that tall. Scroll down, scroll down. That tall. Scroll down, scroll down. That tall. Scroll down, scroll down. That tall. Right? You guys got yourself and all your friends in your calculator? Right? You guys got all this? Right? Hit stat var. Yep. I got 5 people. Scroll to the right. X bar. Right? That's the first box right here. It says what's the mean height. So I'm gonna write that number right here. Does everybody have their mean height right here? Everybody's got that? Right. Scroll to the right again. S standard deviation. Got like that. I guess it rounds to. Okay. Right? Right, you guys good? Right. And here's the last thing today. We're gonna find your z-score. Right. Now remember your z-score is take your own personal height, subtract the average, and divide by the standard deviation. Okay. So my height minus the average, all divided by the standard deviation. Okay. And you'll get a z-score. And the very last thing today is we're going to find out what percentage people are taller than you. Okay. So find your z-score on the table. So mine's 0.38. So 0.3, then scroll way to the right for 8. So 0.38 is right here. I'm seeing 0.648. Right? So 0.648. Right? Now that's how many people are shorter than me. 64% of people are shorter than me. Guys, if 64% are shorter, then how many are taller? Yeah, there you go. Just take 100% and subtract that. Now tell me something like that. Okay? That's the last thing today. Right? Okay. So let me say that again. So you found your z-square by taking your personal height, subtracting the average, and then dividing that by standard deviation. How many standard deviations? You took that value, went to the z table. 0.38 was mine. So here's 0.3. Scroll way to the right to get to 8. So 0.38 is right here. Now this tells how many people are shorter than me. It's like 64 point something percent. So then last thing I did was I took 100% of people, subtract 64.8% who are shorter than me, and that tells me how many people, what percentage of people are taller than me. Okay. All right. So I said, you guys got sub tomorrow, but then we're gonna do a little bit more stats on Wednesday, set up quantum journals, and then continue with quantum mechanics. Fun times. You guys have a great Monday.